Okay, here is an example. I'm going to go over a few examples in this video. Here is the first example. An equilateral triangle 8 centimeters on a side is in a 6 millitesla uniform magnetic field. The magnetic flux through the triangle is 6 microweber. What is the angle between the magnetic field and an axis perpendicular to the plane of the triangle? Okay, so first I'm going to write down the equation. Phi b, which is magnetic flux, equal to magnetic field times BA cos theta. Okay, so theta indicates the angle between B and A. You need to imagine this in 3 dimension. Assume that this is I'm drawing a 2-dimension picture here, but you need to assume it in 3 dimension. Okay, that this indicates that magnetic field is going into the screen. Okay, so if you assume that this is in x, y, and z dimension, so this is x-axis, y-axis, and z-axis. So magnetic field is going into the board or into the screen, so it is on the x and z axis. Now the triangle is placed something like this. Okay, I'm drawing it in 2 dimension, but there is an angle between B and A. So where theta is angle between, I'm going to write it down. So theta is angle between B and normal to the area. Okay, I draw only 2-dimension diagram. You need to assume that this is in 3 dimension. Okay, and there is some angle. Now I know everything, I mean most of the things other than theta. So phi b, which is 6 micro, equal to 6 milli, and area of an equilateral triangle is square root 3 by 4 a square, where a is the side. Here is the a, times cos theta. Okay, and a is given, a equal to 8 centimeter. Convert that into meter. Okay, so I will end up with 6 micro over 6 milli, 6 times 10 to the power of minus 6 over 6 times 10 to the power of minus 3 times square root 3 by 4, and area is 0.08 whole square equal to cos theta. So cos theta equal, so after simplifying this, I end up with cos theta equal to 0.36 and theta equal to cos inverse of 0.36. I end up with 68.8 degrees. That's the answer for this question. Okay, the next one here, which circuit has highest time constant? Okay, for RL circuit, time constant is tau equal to L over R. That's the time constant for RL circuit. So let me take this as circuit 1, circuit 2, circuit 3. Actually he gave us ABC. Probably I can follow ABC. I didn't realize that. Okay, first we'll find tau for circuit A. For circuit A, time constant tau equal to L over R. What is the total R I have? Total R I have is R, and total L I have L in this circuit. For the circuit A, that's L over R. Okay, when you're finding R, make sure that you're finding equivalent resistance when we're looking from the L point of view. I mean, when we're solving circuits C, I'll tell you. So circuit B. So here, what is the total inductance? Here is a good thing. Now, I never discussed in any one of the previous videos. I'm going to discuss a little bit deeper here about the inductors. Now, here I can clearly see the inductors are in series because same current is passing through these inductors. Since inductors are in series, L total equal to L1 plus L2. So if you remember, two let me write it down. Two inductors are in series, L1 and L2, L total equal to L1 plus L2. If two capacitors are in series, C total here, if you remember, this is C1, C2. If these two are in series, it's 1 over C1 equal to 1 over C total equal to 1 over C1 plus 1 over C2. If two resistors are in series, R total equal to R1 plus R2. So for resistors and inductors, it's the same formula if they're in series. Now I'm going to do parallel. I mean, this explanation is not related to this, but it's useful down the line. So if two resistors are in parallel, we know that R1, R2, R total, or 1 over R total equal to 1 over R1 plus 1 over R2. Okay. Same way, when two capacitors are in parallel, C1, C2, here C total equal to C1 plus C2. So for capacitors, we're going to use the opposite formulas. When it comes to inductors, okay, 1 over L total equal to 1 over L total equal to 1 over L1 plus 1 over L2. Okay, so if capacitors are in series or parallel, or inductors are in parallel or series, this is the formula we're going to use. Okay, so for circuit 2, what I'm going to do, since these two are in series, I can say that's R, that's L total. Okay, so tau for this circuit 2 is L total here is 2L. Okay, tau equal to 2L over R. Okay, remember, important thing is R, you're going to find it by looking at the inductor point of view. For the third circuit, circuit C, these two are in parallel. Can I say this is R by 2? Okay, total resistance is R by 2 because R total is R1 plus 1 over R1 plus 1 over R2. I can write this as, or I can write this as R total equal to R1 times R2 over R1 plus R2. That's a simplification. So if both the resistors are same, it's R divided by 2. Now for circuit C, this is circuit B. Okay, for circuit C, I have, this is R by 2 and L tau equal to L over R by 2. Okay, so this is going to be 2L over R. This is circuit C. So which circuit has lowest time constant? I believe circuit A has the lowest time constant. Okay, let me go over the next example here. Okay, here is the next example. In this example, he's asking about which circuit has highest current. Okay, let me label them as circuit 1, 2, 3, and 4. Okay, looks like there are 2 more in the back, but yeah, I will go with these 4. You can find the rest in your homeworks or in your homework. Okay, so the first one, I'm assuming every resistor has the same value, R, and L, R, and L. Okay, so question is, which circuit has the highest current? Now immediately closing the switch. So we'll see 2 cases. First case is case 1, immediately after closing the switch. So the first case, I'm going to see immediately after closing switch. So immediately after closing switch, what is the behavior of the inductor? It acts like a open circuit, assuming these inductors are not fully energized not fully energized initially. So here L, inductor acts like, okay, so inductor acts like an open circuit immediately after closing the switch. Okay, I'm assuming switch is closed at t equal to 0. Now that is called transient state. The transient state is only for few milliseconds. Some circuits might have only microseconds. Okay, for sure it's less than a second. Immediately is nothing but what's going on when I turn on the switch or turn off the switch. That small period immediately after turning on the switch, what is going on inside the circuit, that state is called transient state. Okay, so it's as I mentioned, it's going to be only a few milliseconds. So immediately after closing the switch, so this is going to act like a in circuit 1, I equal to, these two are in parallel, so total resistance R total equal to R by 2, right? So V over R by 2, so 2 times V by R. That's our current for circuit 1. Circuit 2, okay, circuit 2, for circuit 2, immediately closing switch, this is going to act like open circuit, L is going to act like open, so the current is going to pass through this, I equal to just V over R, okay, in the second circuit. When it comes to the third circuit, inductor is going to act like open, but still the current is going to pass through this, so you will end up with I equal to V over 2R. Those two are in series. Okay, in the fourth circuit, I equal to V over, what is the total resistance here? Inductor is going to act like open circuit has a resistance of infinite, so V over infinite, that value is going to be 0. I mean, resistance of a open circuit is always infinite. Now, which one has the highest current? The first circuit has the highest current. This one has the highest current. That is immediately after closing the switch. Now, I'm going to talk about second case. The second case, I'm going to say after a long time. Okay, after a long time, that long time is probably after 2 seconds, 1 second, 1 second. After 1 second, we can call it as after a long time. Now, after a long time, what is going to happen here? Inductor is going to act like a short circuit. Okay, once it is fully energized, L inductor acts like a short circuit. That is called steady state. Okay, that's steady state. Now in steady state, what is I in the first case? In case 1, you have a resistor, inductor is going to act like a short circuit, resistor, and a voltage source. Okay, so this is short circuit. Resistance, some resistance parallel with short circuit. What is that resistor? 0. Here short circuit resistance is 0 ohms. So these three are in parallel, are total equal to 0 ohms. Now what is I? I must be V over R total. You will see infinite. That's theoretically. Practically, if I use this as a W battery has, it can supply only limited current like 2-3 amperes, so probably it will supply 2-3 amperes, but it is going to damage the battery because you're kind of short circuiting the battery. Especially if you touch the ends, it's really hard. We cannot touch it. Okay, so that's a huge amount of current. Second case, so inductor is going to act like a short circuit. So basically in this case, these two are going to act like parallel. So I equal to V over R total. R total is nothing but R by 2. Those two are in parallel. In parallel, it's R by 2. So 2 times V over R. Okay. Third case, we look at third case. In third case, inductor is going to act like a short circuit. So here is a short, here is a resistance. A short circuit parallel with resistor. Can I ignore that resistor? We can ignore this because this is 0 ohms, this is R ohms. R ohms parallel with the 0, you will end up with 0 ohms. Okay, so here I equal to V over R. That's the current. In the fourth case here, so this is going to act like a short circuit. So I equal to V over 2R, since those two are in series. So still, which circuit is going to supply more current? So, even in steady state, circuit 1 is going to supply large amount of current. In transient state, circuit 1 is going to supply large amount of current. Okay, here is the last example. A radio can turn into a particular station frequency by adjusting the capacitor in an LC circuit. So you have a LC circuit. Okay, what happened in LC circuit? These both store energy, so current is going to oscillate between these two elements. So one time it's going to go in one direction, another time it's going to go another direction. So energy is going to be oscillate like a sinusoidal waveform. Okay, now, so it's a RC circuit. Now C value is given. Hold on. So suppose that minimum capacitance of a variable capacitance is in a radio is 4.15 picofarad. What is the inductance value of a coil connected in this capacitor if the oscillation frequency is? So basically he gave us the frequency. In LC circuit we call that as resonant frequency. That value is omega naught equal to 1 over square root of LC, or F naught equal to 1 over 2 pi square root of LC. Okay, so he gave you F naught. Omega naught is in radians per second. This is in hertz. So he gave you in hertz or megahertz. So that value is 1.68. Mega is 10 to the power of 6 times 2 pi equal to 1 over square root of LC. The question he's asking about corresponding one end of the AM radio broadcast band. When the capacitor is set to the minimum capacitance, what is the L value? So what is the L value here? Can I say square root of LC equal to 1 over 2 pi times 1.68 times 10 to the power of minus 6. Actually that's plus 6. Okay, so L equal to 1 over 2 pi times 1.68 times 10 to the power of 6 whole square times C. C value is given, which is 4.15. Pico is 10 to the power of minus 12. Okay, and find the L value. Thank you.